Hello everyone. In this video, we'll look at several practical techniques for modeling electronic components in ANSYS. I will demonstrate them using three typical examples. The first is an SMC package, the second is a QFP package, and the third is a cylindrical capacitor. Although these three cases have different geometries, the workflow is similar. First, clean up the geometry, then control the mesh in critical regions, and finally choose a more efficient method based on the component's structural characteristics. Let's start with the first case, the SMC package. Before starting the actual work, increase the model precision so that small features and connection details are recognized more reliably. This will also make the following operations easier. Set resolution to 0.1. Set tolerance to extra fine. The first step is features cleanup. Here, the priority is to remove the logo on the model surface. These features usually do not contribute to the analysis. In fact, they can significantly disrupt the mesh flow, so it is recommended to remove them first. If geometry adjustment is needed after remove logo, for example to flatten a surface, you can delete and recreate the faces. An efficient approach is to use Select Multiple in Direct Edit to select the relevant faces, then execute delete. Then use Fill from the right-click menu to rebuild the region. The resulting surfaces are usually cleaner and more suitable for subsequent mapping and solid mesh generation. Next, perform fuse. As you can see, the pins are not connected to the body, so fuse is needed to create proper connectivity while preserving the original details as much as possible. For the parameters, keep tolerance set to extra fine. Then choose a relatively small fuse distance, for example around 0.05. The rule is simple. Make the connection, but avoid excessive merging. After the geometry is cleaned up, move to Map Block, which is the solid mesh generation stage. Here, set the global size to 0.1 millimeters and enable 2 rows to control the layers in the pin region. Next, use AutoSplit to partition the geometry for mapping. In the pin region, it is recommended to combine plane cut, perimeter spacing, and pattern mesh. This makes the mesh more regular. Since these regions usually have repetitive structures, once one area is adjusted properly, the same approach can be reused in many other areas. First, use plane cut to partition the region. Then use perimeter spacing to define the number of nodes, and combine it with pattern mesh to generate a more structured mesh. Once the pin region meets expectations, you can freeze this part of the mesh first, then execute update. This way, when making overall adjustments later, the mesh in the critical region will not be disrupted again. If your focus is only on the pin region and there are no strict requirements for the body mesh can be coarsened. For example, place no specific requirement on the number of rows, moderately increase the overall size to 0.3 millimeters, and then mesh the entire model at once. This ensures the quality of the critical region while avoiding an excessive overall mesh count. The second case is a QFP package. Compared with SMC, the problems with this type of model usually arise not in the main body, but in the connectivity between the pins and the body. For the initial settings, it is likewise recommended to increase the precision. The first step is still to handle the logo. For this logo, it is recommended to use Show Only and then delete it manually, which is faster and cleaner. The second step is to handle the pin connectivity. It is recommended to select one instance in the model browser, then manually apply fill and plane cut. This step is not only for filling surfaces, but more importantly, for preparing the mesh flow for the following steps. After processing, right-click in the model tree and run DM Sync to synchronize the current changes back. Then perform connect to clean up penetrations, overlaps, or surfaces with improper connectivity. Next, enter map block. Here, the global size can be set finer according to the size of the pin region. For example, use 0.07 millimeters, select quadrilateral elements and keep at least 2 rows of elements. In practice, rather than processing all the pins at once, it is better to take just one pin, manually build its mesh, and carefully refine it into a template. Here, it is still recommended to use perimeter spacing together with pattern mesh. Once the mesh quality of one pin meets the requirements, use isolate similar groups to identify similar regions. Then use copy entities to copy the processing result, which can greatly reduce repetitive operations. Then freeze the mesh in the pin region before processing the 4 large faces connected to the pins. Use Cut and Create 4-sided to organize these areas into 4-sided regions that are more suitable for mapping. At this point, the subsequent mesh quality will be much more stable. After update, the entire model is ready to mesh, allowing the solid mesh to be generated in one step. The third case is a cylindrical capacitor. Unlike the previous 2 more planar structures, this model has very clear axial symmetry and layered characteristics. Therefore, the processing approach should also change accordingly. For the initial settings, the same approach as before is recommended. The first step is features processing. Here, the focus is not the logo, but the fillet transitions. Use fillets, sharpened to simplify the fillets first. The purpose is to make the boundaries clearer and make subsequent layering and circumferential mesh control easier. Next, proceed to solid mesh generation. Use Stack Mesh. Stack Mesh is more suitable for this type of geometry, with clear layering and axial patterns. It can generate the mesh along the model's stacking direction. A very practical tip here is to control the mesh count by adjusting step length. If the default step length is too fine and results in too many elements, efficiency will decrease. So here, do not only check whether the mesh can be generated, but also whether it is reasonable. If you are not satisfied with the generated solid mesh, go to the Stack Mesh category in the database, open it, right-click, and execute Erase Solids. If you need to adjust the mesh count, go to Redistribute. For example, change the parameter from 0.5 to 1. This will reduce the count. In addition, we can edit and adjust the base mesh, for example by using Pattern Mesh Circular to create a more structured circumferential mesh distribution. After adjustment, right-click and execute mesh. If the mesh meets the requirements at this point, use Delete Except Solids to delete the temporary base mesh. Keep only the required solid results. Finally, to summarize, although the focus differs across these three cases, the core workflow is consistent. First, perform geometry cleanup and simplify unnecessary features. Small features such as logos, which contribute little to analysis or mesh control, should be removed or simplified early to lay a more stable foundation for meshing. Second, prioritize mesh quality in the regions that are most important for the results. Pins, for instance, are usually a key focus during modeling. The mesh quality in these areas should be controlled first. Third, the method should be selected according to the structural characteristics of the component itself. For planar packages, you can make greater use of repetitive structures and mapping strategies. For cylindrical and layered components, it is more suitable to process them based on their axial and layered characteristics. In addition, if this type of modeling work is common in a project, these steps are also very well suited for gradual integration into ANSYS automation workflows. ANSYS secondary development is mainly implemented through the Python-based ANSYS API. You can write and debug directly in the script editor. You can also develop using VS Code. Therefore, repetitive tasks mentioned earlier, such as feature cleanup, pin region processing, and solid mesh generation, can gradually be converted into automation scripts or tools to further improve efficiency. That concludes this video on ANSYS modeling strategies for electronic components. Thank you for watching.